What's poppin' party people? Welcome back to another day of geometry. Today we're going to be focusing on the area of regular polygons. But before we jump into it, you've got two warm-up problems here. So problem one, problem two. Go ahead and pause the video and try these problems on your own. All right, we're back with some answers. Let's check your work and see how you did. All right, so for problem number one, breaking up that shape into a isosceles trapezoid and a rectangle, finding the areas of each, add them together, and you get 339 square feet. And for problem number two, it is just a matter of taking your area formula for trapezoids and plugging in all of the information that you were given, solving for the second base, which we find to be 12 meters. All right, let's push forward now into the meat of what we're doing today. All right, so we got a whole bunch of stuff we got to summarize and fill out and get some vocab down, but let's just jump into it. Some of these things you might know, but we're going to start giving some definitions here for the objects that we're going to be discussing. All right, so a regular polygon is an equilateral and equiangular shape formed by a closed chain of segments. So really what that means is that it's a shape that doesn't have any big gaps missing or just sort of like swinging open. It's a closed figure made from a chain of segments. All right, all these segments are going to be congruent, right? All the sides of the shape are congruent, and as a result, all of the interior angles are going to be congruent as well. All right, so that's what we're talking about when we say a regular polygon. All right, polygons also have different names based on their numbers of sides. So for example, you might know that a pentagon has 5 sides. All right, you might also know that a hexagon has 6 sides. And you probably also know that an octagon has 8 sides. All right, what you might not know are some of the other names of some of our regular polygons. So a heptagon has 7 sides. A nonagon, you might be able to guess this one, has 9 sides. And a decagon, if you know your, Latin and Greek roots and prefixes, a decagon has 10 sides. All right. In addition to this, we also need to have some vocab around different segments and parts of a regular polygon. All right. So the circum circle is the circle that can be drawn going through all of the vertices of the regular polygon, right? So to remind you, a vertex is a point, like a corner of the regular polygon. And so what we're saying is that the circum circle is a circle that goes through all of those vertices. All right. The incircle is a circle that can be inscribed inside that regular polygon. But the 3 vocab terms, the 3 segments that we really need to get down, these are probably going to be the most important ones that we use, are going to be the radius, the apothem, and the side. All right, now I'm not going to define side for you. I know you know what that means. The radius is a little bit different from how we normally think of radius. It is still indeed the radius of a circle. It is the radius of the circumcircle, but in the context of talking about regular polygons, when we say radius, we're going to talk about the segment from the center out to the vertex. Right? That's what we mean when we say radius. Right? The apothem, which you might also hear referred to as an apothem. I'm going to say apothem, but both pronunciations are, generally accepted. But the apothem is the segment from the center of the polygon out to the midpoint of the side. All right, and it's going to be perpendicular with the side of the regular polygon. So that apothem is doing 2 things. It is bisecting our side, and it is forming a right angle. It's perpendicular to the side. All right, that's what our apothem does for us. So these are the 3 terms that you're going to need to know: radius, apothem, and side. All right. And one last thing before we get to how we're going to talk about area for this regular polygon. One thing that we need to be able to do is find the central angles of all of these polygons, which you might memorize because they're not going to change from here on out. But I'm going to show you a technique where you don't actually have to memorize it at all. So let's take a look at that. All right. In order to find the central angle, I'm going to draw a circle that circumscribes our pentagon. So you can see just about there that we have a circle surrounding our pentagon. All right. From the center, I'm going to draw some radii. Right now, remember, a radius of a regular polygon goes from the center out to a vertex. So I'm drawing in some radii. Right, and some things that you might notice are that all these radii are going to be congruent. And because we said that this was a regular polygon, we also know that all the sides of the pentagon are likewise congruent. So if you're looking at this, you can see 5 congruent isosceles triangles that make up our pentagon. All right. Now, because all of these triangles are congruent, that means that all of the central angles, so here, there, right, all those angles are going to be congruent. So in order to find the measure of those central angles, we're going to take the entire measure all the way around, that 360 degrees that we get around the circle, and we're going to divide it by 5. So 360 divided by 5, you can check in your calculator, is 72 degrees. All right, that means that the central angle for all of these triangles is 72 degrees. All right, we can do the same thing with the hexagon. I'm not going to draw the entire circle, but you can imagine that it's a similar product as what we did up above. So here, 360 divided by 6, resulting in a central angle of 60 degrees. All right, we can do it again for our heptagon. So draw on the central angle. 360 divided by 7, right? 7 sides, 7 central angles. And we're going to get about 51.43 degrees. For our octagon, drawing in our central angle, we do 360 divided by 8, which is going to be 45 degrees. 360 divided by 9, giving us 40 degrees. And then 360 divided by 10, giving us 36 degrees. All right, so again, you can memorize the central angle measures if you want, but really when it comes down to it, you can just take 360, divide by the number of sides, and use that central angle as needed. All right, 72 degrees. So now let's talk about the ways in which we can find the area of a regular polygon. To do that, I'm going to switch to a different window. Shablam, just like that. All right, let's take a look at this regular pentagon that we have in pink. All right, you can see that we have split up that regular pentagon into 5 congruent isosceles triangles, just like we did back in the notes. All right, one thing that I'm going to do here is draw in the apothem. So there's our apothem. All right, remember the apothem from the center to the midpoint of the side, and it will bisect that side, and it is perpendicular to that side. All right, so we're drawing in our apothem here. The next thing that we're going to do, and it takes a little bit of imagination, some visualization, but we are going to sort of unfurl this pentagon. So watch it happen here. All right, we take those 5 triangles and we lay them out just like that. All right. Now notice that the 5 sides of the pentagon, and I'll wind it back so you can see it, but the 5 sides of the pentagon ended up at the bottom of our figure, right? So watch that line in bold where it says perimeter, right? That comes from the 5 segments that were the sides of the regular pentagon. So as we unfurl them, the perimeter, right, those 5 segments on the outside of the pentagon end up at the bottom of our figure. All right, now we're going to duplicate all of these pink triangles, and they're going to show up in yellow. Right, so these yellow triangles, duplicating the pink ones, and we're going to rotate them up above the pink triangles. Right, they're the same size, we just duplicated them, and we're rotating them around so they're on top now. All right, so each of those single yellow triangles is still congruent to one of the pink triangles. And having moved them up, now we are going to translate them down and to the left. Right, it's a little bit of a translation here, sliding on down and filling in the gaps. All right, the last thing that we're going to do with this is notice that once we've translated those yellow triangles, they create a parallelogram in conjunction with the pink triangles. All right, now remember that we originally wanted the area of the regular polygon, that regular pentagon in this particular case, that was made up of these 5 pink triangles. So in order to find the entire area here, we want to find just the area of the pink triangles in this diagram, right? Their size hasn't changed, so we can still find the total area of these pink triangles, and that will give us the area of the regular pentagon. In order to find the area of these pink triangles, though, we're going to notice that the pink triangles are half of this parallelogram, right? Half of this parallelogram. So if we can find the area of this parallelogram and then divide it by 2, that's going to get us the area of just the pink triangles, which, as we said, is the area of the regular pentagon that we were looking for. All right, now the question is, what is the area of this parallelogram? Well, hopefully you remember that the formula for the area of a parallelogram is base times height, right? Base times height. So as we're looking here, remember that this chain of 5 segments on the bottom was the perimeter of our regular pentagon. And now that we've drawn it as a parallelogram, the perimeter of the pentagon has become the base of the parallelogram. Right, if we're talking about the height, that would be the apothem of our pentagon, right? The apothem of our pentagon. So, as I switch back to our notes, right, what we wanted was the area of the parallelogram, and then we would divide by 2. Hopping back into my notes, here we go, all right. What we wanted was the area of the parallelogram, and then we would divide by 2, right? So remember, area of the parallelogram is base times height over 2. But we said that in this particular case, the base of our parallelogram was the perimeter of the pentagon, and the height was the apothem. And in the end, we divide by 2. All right, so that's how we're getting to this area formula, that the area of a regular polygon is equal to the apothem times the perimeter, all divided by 2. All right, so here's what we're going to do. I have got 2 example problems down below. All right, so find the area of this regular hexagon, find the area of this regular octagon. All right, I want you to just try it on your own. See what you can recall from what we did previously, some of the techniques that we've been doing in this unit, and how you can apply them in this formula. Right, area is equal to apothem times perimeter divided by 2. Try these problems out, pause the video, and come back when you're ready. All right, so I'm going to just show you the answers up front. So if you've tried these problems and you feel rock solid with your answers, you know, terrific, and hopefully you are golden with it. But otherwise, we'll push forward and I'll show you the solution. All right, so the first one, 216√3 centimeters squared. For the second one, 636.4 inches squared. All right, let's talk about how we got those answers. So in order to find the perimeter of this regular hexagon, I need to know one of the sides, right? We already know the apothem, so half of our formulas are already taken care of, but we need to know one of the sides. In order to do that, I'm going to draw in this radius so that we end up with this right triangle, right? That right triangle is going to be very useful for our purposes in finding the side of this hexagon, right? Reason being is that if we find this angle, let's say theta, right, we already have one side. So with one side and one angle of a right triangle, we can use some trigonometry to get the other lengths that we need. All right, the question then is, what is that angle theta? All right, well, if we think about the central angle, right, of this regular hexagon, we said that we could find that by taking 360 and dividing by the number of sides. So this entire angle, if you take 360 divided by 6, is going to be 60. But we know that we have an isosceles triangle, and the apothem is serving as the altitude, which, if you recall, bisects the angle at the vertex, right? It's going to bisect that central angle. So if the entire central angle is 60, we can get rid of all that. If the entire central angle is 60, that means that this angle here is 30 degrees. As a result, we have a 30, 60, 90 right triangle. And so if we have 6 root 3 across from our 60-degree angle, that means that we're going to have a length of 6 across from our 30-degree angle. And so, because our apothem bisected this side, the entire side of this regular hexagon is 12. All right, so now we have all the pieces that we need in order to solve for our area. All right, so again, I'm going to write this formula down just for good practice, good measure. But area is equal to, we'll color code it here. Let's go green. It's equal to the apothem times the perimeter all over 2. All right, so we know the apothem because that was given to us. The apothem is 6 root 3. All right, the perimeter we can get by multiplying the length of one of our sides, which we found to be 12, by the number of sides that there are in this regular hexagon. So in this case, 6. All right, and all that is still over 2. And now it's just a matter of simplifying. So 12 times 6 root 3 all over 2. I know that nothing's going to affect my root 3, so I can just look at the 12 times 6 over 2. And in my calculator, I can go ahead and punch that in. I'm going to find that that is 216. We'll keep the root 3. All right, don't forget your units, centimeters, and we're talking about area. So centimeters squared. Oh. All right, but there's our answer. So now let's talk about our next example. Determine the area of the regular octagon below, round to its nearest tenth. All right, we're going to do a similar thing here. So I'm going to draw on the apothem because we need it to make that right triangle. And then we can think about what the central angle of this octagon is. All right, so 360 divided by 8 is going to be equal to 45. The angle that we need for this right triangle is going to be half of 45. In this case, that means 22.5 degrees. All right. And so with that right triangle, what we're looking for is this apothem, we can call it A, right? And then this little half side down here, we can call that S if we want. Right, and we're going to base that off of our 15 inches. So from our angle of 22.5, I'm just going to label some sides so that we know what we're doing with our trigonometry. Our 15 is the hypotenuse. This A works out nicely. It is the adjacent side. And this S is the opposite side. All right, so if we are trying to find, let's say, the apothem first, then with our adjacent and hypotenuse, we are going for cosine. All right, cosine of 22.5 degrees is equal to the adjacent side, our variable A, we don't know it yet, over the hypotenuse, 15. So in order to solve for A, we're going to multiply by 15 on both sides, and that way our 15's reduce on the right. So A is equal to 15 times cosine of 22.5 degrees. All right, I'm going to hold on to that answer. I'm not going to punch it into the calculator just yet. I want to hold it so I get the most exact-ish, because we are rounding, but the best answer possible. All right, I don't want to round too early and get a rounding error. So there's our apothem A. Go ahead and shrink this up a little bit, drop it over there. Now I can move forward and find that half side, which we said was, you know, a variable S. Really doesn't matter. You could pick whatever letter you want. All right, but we're working with the opposite and the hypotenuse now. So that means that we're working with the sine function. Sine of 22.5 degrees is equal to the opposite side, our variable S, over the hypotenuse, 15. And we're going to do the same thing that we did before. We're going to multiply by 15 on both sides. And that way the 15s on the right will reduce out, and we're just left with our variable S, which we are trying to solve for. So here, S is equal to 15 times sine of 22.5 degrees. All right, what that means for us is that if we are trying to find the entire side of our octagon so that we can find the perimeter, we're going to take this S and multiply by 2. Right? So 2 times 15 sine of 22.5 degrees, which with the 2 and the 15, we can just call that 30. All right, and now it's time for us to solve for area. So area of our octagon is equal to the apothem times the perimeter all over 2. All right, we know that the apothem is 15 cosine of 22.5 degrees. We know that the perimeter is going to be 8 times whatever side we had before. So that's going to be 8, because it's an octagon. We found that the side was 30 sine of 22.5 degrees. Right, and all of that is getting put over 2. And so now I can hop into my calculator and go ahead and punch that in. So let's hop on over to the calculator. All right. I've got a fancy fraction going on here. And honestly, I just love excuses to use fancy fraction. So fancy fraction, 15 cosine of 22.5 degrees times 8 times 30 times sine of 22.5 degrees. And all of that was over 2. So enter. There we have it, 636.4. So let's hop back to the notes just to get it written down. All right, from our calculator, we had 636.4. Again, make sure you're rounding to the appropriate decimal place. In this case, it was to the nearest tenth. Our unit was inches. We are talking area, inches squared. All right, so thank you for coming on this math journey with me today. The last thing that you're going to need to do is to upload these notes into Canvas. But other than that, we are good for today. We'll pick up on a little more area of regular polygons tomorrow, but I hope you have a wonderful rest of your day. I will see you next time.